Okay, guys, we are at Scaling Ethereum Hackathon. My name is Lisa, and I'm happy to introduce you to Taiko. Taiko is a fully decentralized Ethereum equivalent ZK rollup that is a Type 1 ZK EVM. And let's quickly define what all that means. So, a rollup is a layer 2 scaling solution that batches multiple transactions of chain and submits them to a separate chain in a single transaction. For example, to Ethereum. So it batches multiple transactions and submits in a separate transaction, one single transaction. That's why it's a scaling solution. And the ZK rollup is just a rollup that uses zero-knowledge proofs, also often called validity proofs. When we say Ethereum equivalent, that means that there are no changes to the way Ethereum clients execute bytecode and store data. That is, Taiko uses the same hash functions, the same state trees, transaction trees, precompiled contracts, and other in-consensus logics, and it will inherit future Ethereum upgrades further. And decentralized in the rollup context means that both proposers and provers are decentralized. That is, no single party is able to control all transaction ordering or be solely responsible for proving blocks. So where we are today, in December, we released an Alpha 1 testnet, and in March, that is very, very soon, we are releasing Alpha 2 testnet. So we are here. Taiko consists of three parties, that is a ZK EVM, and a layer 2 client, and the protocol. And today, right now, we will learn a bit about the Taiko protocol. Let's go. Layer 2 solution rollup bundles some transactions in a block, and then this block goes through three stages: block proposition, block validation, and block verification. Let's start with block proposition. Taiko client determines the transaction sequence in the block. So it gathers some transactions and order them in the block and proposes this block to the Ethereum node. Many blocks are proposed in parallel and pending in the Ethereum mempool. However, for unverified blocks, Taiko supports a limited amount of slots on Ethereum Beacon chain, and we use these slots. Let's suggest we have 10,240 slots, and we use that. That is for block number 10,240. So the block number 10,240 takes the slot 10,240, and after that, the block number 10,241 takes the first slot, takes the same slot that the first block took. And so it's kind of a slot string. And that means that after the first 10,240 blocks were used, the block proposed fee will be minimized as storages are being reused. Proposed block consists of metadata and list of transactions. And metadata is specified according to the Ethereum Yellow Paper. And what is interesting about that metadata is accessible by EVM, by the Ethereum virtual machine. That means accessible for anyone, while the transaction list is not, and the transaction list will be executed on layer 2 only. And that is the core idea of rollup, in fact. Taiko client proposes a block using Taiko L1 contract. Taiko client communicates with Ethereum layer 1, executes transactions, builds new states, updates the Merkle trees, on demand shares the witness with the prover, and can be run by anyone. And Ethereum node determines the final block order on layer 1. That is, when the block is proposed by Taiko client, its parent hash is not specified, meaning that the final block order is fully up to the Ethereum node. After block proposition, we have block validation. This check is executed by Taiko L1 contract, and we have a set of formal rules that a proposed block should pass to become valid. The validation rules for a block include the following. So the first criteria, the transaction list is RLP decodable into a list of transactions. RLP decodable is a standard for data transfer between nodes in a space-efficient manner. Then, criteria number 2 is that the number of transactions in the block is no larger than the maximum number of transactions in the Taiko block minus 1. And this minus 1, this is minus the first transaction in the block, that is the anchor transaction, and we will talk about it later. The criteria number 3 is that the sum of all transactions gas limit is no larger than a Taiko block's maximum gas limit, besides the gas limit for this first transaction in the block, the anchor transaction. Then, if the block is valid, Taiko client downloads this proposed block and converts it into a real Taiko layer 2 block, and it is appended to the Taiko chain block list. So in fact, when the block is proposed, it is not a real block. It's just a bundle of transactions with some metadata. And when it is checked to be valid, Taiko client converts it into a real Taiko layer 2 block. So when we say converts into a real Taiko layer 2 block, it means that after being downloaded, the block is decoded into a list of transactions, and Taiko client validates each transaction and generates a trace lock for each transaction for the prover to use it as witness data, and valid transactions are packed into the layer 2 block, and invalid transactions are dropped. And for transactions, validation rules include the following. The transaction signature is valid, nonce is correct, and the sender's balance is no less than the intrinsic gas, and intrinsic gas is defined in the Ethereum yellow paper. Taiko layer 2 block consists of anchoring transaction and just a list of transactions. And this anchoring transaction is always the first transaction in the block. And this anchoring transaction contains all necessary data that is not covered by the ZK EVM itself. So, while ZK EVM covers signature validity proof for each transaction, state proof, that is a Merkle tree, and the execution proof, that is, given the right inputs, one will get the right outputs with very high probability. The anchoring transaction holds 256 hashes of the latest blocks that are not a part of Merkle tree, and layer 2's chain ID. A bit more details about valid and invalid transactions. If a transaction is invalid, it doesn't make the block invalid. The invalid transaction is skipped in the block. However, Taiko client supports an option to run an invalid transaction to generate a trace for prover. And furthermore, even an empty block is a valid block and still needs to be proven. Final stage, block verification. The prover generates zero knowledge proof and submits this proof directly to the Ethereum node. But it submits it through the Taiko client, and Taiko client provides the prover with the witness data for zero knowledge proof generation. There is no specific ordering for proof generation, so a proof can submit a proof for any block selected. Before being verified, the block should be checked for being valid, and its parent hash transaction should be verified. And right after that, the block is immediately verified. That is, the proof is immediately generated. And if the block is invalid, that is how it works today. If the block is invalid, instead of converting it into a real Taiko layer 2 block, Taiko client creates a temporary block with the only transaction inside, invalid block. And the prover generates the valid proof for this temporary block. But with the next protocol upgrade, things will change, and we won't have any temporary blocks anymore. And with the next protocol upgrade, a prover will generate a proof that verifies a block is either valid or a block's transaction list is invalid. So that's the short story of Taiko protocol.
All right, hey everyone. Welcome to this workshop. My name is David from Taiko. Today we're going to speed run build an Ethereum app, which has some nice tech included. So it has a SvelteKit app. The ABIs and contract addresses are automatically generated and fully typed with WAGMI. It has a Web3 modal connect button using WAGMI core, and it has a Foundry configured as well. So the whole project is a mono repo setup with npm, and it's configured for it to be easy to work on any layer 2 as well. So yeah, let's get right into it. To get to this repo, you can just scan this QR code and it should take you there. So otherwise, the repo link is here, github.com/this. Okay, yeah. So you're just gonna click this blue button for deploy, connect your GitHub account, and create some repository name for the app. You need to set one environment variable. You can just get this from Wallet Connect. This is for the connect button. You need this project ID. Just add it here. And after clicking deploy, you should have an app that's fully functional, and it'll be deployed. So yeah, let's take a look at this repo so we can work on it locally. So first thing we need to do is clone the repo. So I'll just clone it. Then we need to cd into it. Then we need to do this forge install command. Then we need to run this setup script. This will just copy the environment variables and install node dependencies. Then we need to set two environment files, or two environment variables, the mnemonic phrase and the Web3 modal project ID. So you can generate a mnemonic phrase here. It's also inside of the environment variables, which I'll just open right now. Yeah, you can see the link right here. So yeah, you can just generate some mnemonic. It'll create a string of some words that map to wallet addresses. I already have one, and yeah, just yeah, I'll just show it. I don't really care. It only has a little bit of text in it. Okay, so copied that. I'll use this mnemonic. Just share the ETH if you take it. I'll get the wallet connect ID. I'll put it right here. All right. Cool. So yeah, that's the full setup. Just setting those two environment variables, and now we can start the local development environment. So it says we need 3 development windows, and you need to make sure to source your environment. So I'll go ahead and do that. Let's see here, 1, 2, 3. I'll store some environment variables. Okay. There's 2 environment files, one for each, for Foundry, one for the front end. So, okay, cool. So these 2 windows, the first one will start, and all of these commands are just available right here. I just know them, so I won't refer to it. But first we'll start a local Ethereum node, or a local Ethereum chain rather. So this is Anvil. It's supported by Foundry. And now I just created this, I started this Anvil chain locally with these 10 accounts. And these 10 accounts are all populated with ETH. And these accounts were derived from that mnemonic that I passed in. So what you can do is you can take any of these accounts and you can just take the private key and you can go to, you can just go to MetaMask and you can import the private key. So you can use it on your front end. All right, so after starting the local Anvil chain, we can start the web app. And then after that, we can, let's just see what happens first. I think it might not work or have an error. Or it'll have an error if I click that. Okay, cool. So we need to deploy a contract to this chain that we started because it doesn't have one deployed yet. So we have a script for that. It's just like so. And now if you read a message, I need to connect to Foundry network. So now if we read a message, it says hello world right here. And if I actually open up that contract right here and I change it to hello world ASDF blah, if I deploy this new contract and I read the message, you'll see it's automatically updated. So it's not just the contract, like all of the ABIs and types and ways to interact with the contract on the front end are automatically generated as well. Excuse me. So that works with this like wagme generate command. So let's see here. Yeah. So we have a contract, we can interact with it, we can write a new message to this contract. It's just a dummy contract that has a message and you can change the message. Now it gets updated to this new message. Yeah, so that's how you deploy smart contracts in your local chain. You connect to that local chain through your front end and you automatically have all of your ABIs and types, no imports or copy pasting needed. That's all being done in this wagme config TS file where we declare a deployment, this foo deployment, and we just pick up the contract address from the logs of deploying the contract. So let's try to see a little bit more about how this flow works by just creating another contract. So I'll go to this contracts folder in the mono repo. I'll create it. This will just be called bar.sold. It's going to be like exactly the same as foo.sol, except I'll change the message to just say bar. And yeah, let's write a unit test for it as well, just to show how that works. It'll also be the same as like this unit test from foo. We'll put it in here. We'll just rename foo to bar. Yeah, that's about right. Uncomment this bar. Let's run a test to see if this actually compiles. It says what is source bar.sol. Probably because I didn't name this contract correctly. So now if we run the tests, assert failed. It says the message should be hello world, but we're expecting it to be bar. So we will just go ahead and change that. Whoops. And then now the test should pass. Okay, test is passed. So we just wrote a unit test. We just wrote a smart contract. Let's deploy this smart contract. So what we'll do is we'll do the same. We'll have to look at how this deploy works. So if you look at the command, you'll see we run a script called deploy. And we deploy that to an RPC URL, which is Foundry. And then we generate the types. So like, we can easily deploy to other chains too, and maybe we'll show that. But if I go in and I look at this script, this deploy script, I'll deploy another contract now, which is the bar contract that we just created. And it's going to look very similar, obviously. So we're going to deploy bar. Basically, the deployer of this smart contract is the first key in the mnemonic that you generated. So it'll just use the artificial ETH inside of the local Anvil chain to deploy the contract. So here, this is just straight Solidity. We'll just create a new bar smart contract, and yeah, let's deploy this. So now this will deploy both of them again. Says what the heck is bar? Okay, it's this thing. Okay, cool. All right. So now they've both been generated, and the last thing we need to do is inside of our WAGMI config, which is inside of the app folder of the mono repo, we need to declare that deployment for bar. So I will just create that. So we're going to call it bar. The contract address for this chain is going to be the Foundry chain ID. And we just need to import this JSON file, which is an artifact of the log. Run latest JSON. Oh, actually, so the way this is configured is like now there are two. If you look at the broadcast deploy logs and this run latest JSON, you'll see that two were deployed, this foo contract and this bar one. The bar one is the second transaction. So it's a little bit of a finicky setup for this. You don't have to do it this way, but I think it's easier. So if you're just continually deploying your contracts and like testing updates. But what we can do is we have this bar JSON now, and we can take that as the second transaction from the logs. And basically anytime you redeploy a contract, this run latest JSON will get updated. The contract, it'll pull the contract address so that on your front end, you're using the new contract. If you don't want to do it this way, then after you deploy, you can just see what the contract address is, and you can just directly copy and paste that in here, which is how the WAGMI documentation shows it. I just think this is a little bit more of a reactive way. Okay, cool. So we deploy the smart contract. We might need to generate the types again. I'm not sure, but we'll just do it anyways because we just changed this WAGMI config. And now we should be able to use this bar contract. Okay, so how do we use that? Let's go into our app folder. Let's find the component for this first page that we saw. And inside this component, you'll see we obviously get the foo ABI, the foo address. Let's do the same thing, but we'll get the bar ABI. And as you can see, and like as we've said, it's just all automatically generated. So now I have the bar ABI and the bar address. So what I can do is I'll just, how do I want to do this? Yeah, I'll just use the bar. I won't duplicate it. I'll just use the bar ABI and the bar address. So I'll change this to bar ABI, change this to bar address. I think that's everything. Is there, yeah, foo is only up here. Okay, so now we're going to use the bar contract in our front end. So the way that we can test that is bar was initialized with this thing bar right here, right? So will it say bar? Yeah, it says bar. Okay, cool. So now we can update this smart contract and maybe. Okay, cool. And now we just updated the state of this bar contract that we just deployed. So just to hammer it home, we can literally just update this to something else. We can go ahead, go down here. We can deploy the contract. It'll know what the new address is of the deployed contract. All of the ABIs and everything will be typed. And now if we read the contract, it says this crazy thing that we just put in there. Okay, so we wrote a unit test. We showed how you can deploy to your local chain. Now, if you want to deploy to another chain like let's say Taiko, for example, I think I have Taiko set here. Yeah, we have this hackathon RPC. So if I want to just deploy this to Taiko, I literally just change the Taiko. Or I could change this to Optimism, or I could change this to Scroll, or I could change it to Base. You get the point. It's like, it's just easy to deploy like essentially anywhere. Okay, Taiko doesn't have this EIP 1559 enabled, so I need to do send the transaction in like legacy mode. I think I'm supposed to put this over here. This is just deploying the bar contract to Taiko. All right. It's not going to be as fast as the local chain, but yeah, it'll deploy it. Okay, so now just for full coverage, we showed how we can write a unit test and write a smart contract, how we can add that smart contract into our deployment script by just initializing it like this, and how our front end automatically knows the configuration to interact with that smart contract, and we updated that. So let's see here. Is there anything else to talk about? It is supposed to be a speed run. All right, yeah. So yeah, that's the basic directory structure for Foundry. It's just script, source, and test. If we look inside of the packages folder, like I said, the main thing is that wagme config file, which is kind of like declares your smart contract configuration so your front end can use it. Yeah, it's pretty straightforward. I mean, that's about it. You can just start building smart contracts and start consuming them in your front end. And yeah, that's about it. Svelte has very good documentation, so I won't go into how to build on it, but it's very, very simple, so I don't think you'll have trouble with it. And we have these stores that you can use. So if you need to access the wagme client or a provider or anything like that from within any kind of file, you can just go in and you can just do like an import, let's say providers from stores here. Yeah, and then you can access it. You can access that store, like maybe you can do something like this, and then you can do it. Yeah, I think you can access this store by chain ID, and then, yeah, let's do get balance. Do we need to provide an address? All right, yeah, let's do balance of this address. Alright, we need to wait for it, I guess. Foundry get balance. Yeah, this is an async function, so... Okay, so let's just do like async function get balance here, and then we'll just call this. I mean, the main point is that you can just access this provider from like anywhere, but we'll do it anyways. Const balance is equal to that. Balance and take a toString. I don't know if it does. Okay. And then on mount of the component, shout out ChatGPT though. Maybe doesn't know what on mount is. Oh yeah, I think this is imported from the wrong place. It's probably just supposed to be from like there, maybe. Okay, cool. And here's our balance. Okay. Anyway, so you can use the stores to access like global state. Let's talk about the next part of this app, which is this signal service tab over here. So basically, Taiko has some really elegant properties just because it's Ethereum equivalent. So one of those is the ability to like build a bridge on top of the protocol. So the bridge is built on top of this very simple signal service, but let's just show how it works, and I think it'll make sense. So step one, it says here, connect to Sepolia network. And then what we can do is we can store some signal on Sepolia. So that's just writing some data to a smart contract called signal service that we have deployed on Sepolia, and anybody can use that. So I'll just send this signal from my address. And basically, after I send that signal, the thing is Taiko and the base chain, like Ethereum or whatever, keep track of the respective block hashes. And because block hashes look the same on Taiko, because Taiko's blocks look the same as Ethereum blocks, it supports Merkle proofs. So what we can do essentially is we sent a signal to this base chain, Sepolia. And now we can ask some Sepolia node to generate a Merkle proof, to just prove to me that I I sent this message somewhere inside of the state, or I stored this inside of the state, and I can take that proof and I can verify it on Taiko. I can actually make a call to Taiko, verify that Merkle proof, and it can check if that message was received on the base chain just by checking the its hashes, because it keeps track of the hashes of the other chain. So this is a signal that I haven't sent before, so it'll say signal received is false. And here is one that I have sent before, so it will say signal received is true. And yeah, you'll have to wait about like 5 minutes. Like it'll take 5 minutes before this one returns true, because the time in which like we're deriving blocks onto the L2 is configured at like 5 minutes currently. It's a configurable variable, but we just set it that way so we don't burn through too much ETH, Sepolia ETH. And yeah, so we're really hoping you can build on top of this. You could actually build a bridge yourself on top of the Signal service. So yeah, I think it's a really cool solution for like cross-chain messaging, and there are some cool app ideas here, especially bridges. Okay. Yeah, so we went through the application. We showed how easy it is to deploy contracts and work with them. And yeah, it's that's really it. That's really that simple, I guess. And yeah, if you need any help at all, please just reach out to us on the Discord. We'll definitely be happy to help with like anything that you're trying to build. You can reach out to me directly. My name's Dave, as I was saying, if you want as well. And yeah, happy hacks. I'm looking forward to some cool projects. Here's the repo URL again. And yeah, and thank you very much.